All right, welcome to talking about polynomial inequalities. Here's the deal. We've done a lot of this in the past. We're just going to take it to the next level. We have a function here, 2x cubed plus 9x squared minus 5x, and we want to know when it's at least 0. So basically, we're going to take the function 2x cubed plus 9x squared minus 5x. We're going to say, when is it at least 0? So greater than or equal to 0. Well, we'd love to factor this then. This is a great review from what we've been doing. So basically, if we take an x out of everything here, we will be left with 2x squared plus 9x minus 5. And that'll be greater than or equal to 0. That's fine to do when this side is actually 0. So now I would like to try to factor. Teach me how to factor. Teach me how to factor. And then we got 2x. Looks like if I put a plus 5 over here and a minus 1, that's going to work out just fine. Okay, so here's the deal. I have zeros at x equals 0. I have another 0 at x equals 1/2. And then I have another 0 at x equals -5. So what I'm going to do over here is I'm going to sketch those on a number line. So I'm going to put my -5 obviously over here. Then I'm going to have 0 here and 1/2, not necessarily to scale, but those are my zeros. Okay, so the idea with the polynomial inequalities is we want to shade the areas where this function is greater than or equal to 0. Well, without going and graphing that right now, what we could do is we could just algebraically test values, okay? So here's the deal. Pick any value you want. I'll pick a value way over here, like let's say the value 10. If you go right into this, we're going to have the product of 3 numbers. Well, if you look here, if we put a 10 in there, that's going to be a positive value. Remember, this is where we do the positive negative testing. So that's going to be a positive value times, if we put a 10 in here, 2 times 10 minus 1, that's going to be a positive value as well. And then putting a 10 here is going to be a positive value as well. So if we take a positive times a positive times a positive, we will get a positive region in here, okay? Well, 1/4 would be the number, one number I could pick in here because of the boundaries being 0 and 1/2. So if I put 1/4 in the front here, obviously I'm going to have a positive. If I put a 1/4 in here, well, 2 times 1/4 is going to be 1/2 minus 1. That's actually going to give me a negative. And then 1/4 plus 5 is going to give me a positive number. So if I have a positive times a negative times a positive, this is actually going to be a negative region in here. If we pick -2, -3, anything in here, so -3, we're going to get a negative. Then we're going to multiply, 2 times -3, that'd be -6 minus 1. That's going to be times a negative. And then -3 plus 5 would be a positive there. Negative times positive is going to give me a positive region. And then over here, I'm going to put in -10 million. That would give me a negative right here, times a negative there, times a negative there. Negative times negative times negative, negative region. Now here's the deal. These are what we care about right now. Those are the regions and what they are, either positive or negative. It doesn't matter what you test as far as a value, as long as it's in that region, that's what we're going to get. So basically, when you're looking at this problem, you got to look right here. It's telling you we want, actually, that's probably not the best place to look. You want to look where you have it in factored form in case any signs flipped along the way or anything. So I got greater than or equal to 0. Well, that means I want values that are positive regions because I want greater than or equal to 0. So what that means is we're going to use a bracket in here all the way to there, and then we're going to use a bracket and then all the way to infinity. So my final answer in interval notation would be -5 to 0, and then union 1/2 to infinity. Now, I want you to make the connection here. I set it up here in the directions. Challenge yourself to really connect what is happening on the graph. So I don't mean to mess up the picture too much, but I'm going to go to, black. I want you to pretend right now we were graphing this like we've been all week, and it said equal to 0. Well, this would have been, remember, a cubic function. The end behavior would look like this, and the multiplicities are 1, so they would cross. So think about this. We would put those 3 on there. We would go like this. We would cross, and then we would cross again, and then we would cross again, and we would go up like that. Well, if you look at it, we've got right in here all values as far as the x values that are producing y values that are greater than or equal to 0, including these two because they have the brackets. And then same thing is happening over here. So I've also got that fired up here on the calculator. Hold on. This is what that is graphed. Okay, that first, wait a minute. I don't know if that's the right one. Yeah, it is, sorry. Okay, so I've got this one fired up here on the calculator, and you can see from -5 to 0, all of the values are greater than or equal to 0, and then we have that little dip, but then starting at the 1/2 to infinity, we have them greater than 0. So it's kind of neat to make that connection to understand what you're doing. All right, so let's try some more. Where is g of x less than 0? So here we go, pretty similar to the last one, just new new polynomial. So x to the 4th minus x cubed minus 20x squared less than 0. So again, we're going to take out that GCF, and we'll get x cubed, whoops, sorry, x squared is the GCF. So we will take out an x squared, and we will get x squared minus x minus 20 less than 0, and this one works out with some simple quadratic factoring. So x minus 5x plus 4 less than 0. So again, if I were to go graph this, I would be confident graphing that, but we're asked a little different question here. So I've got myself the -4, I've got myself the 0, and I've got myself the 5. And honestly, if you connect with the graphing well, you should be able to answer this question as well. If you're just cranking out the algebra, I'll go through that again. So let's just pick some values. If I pick, over here is 10,000. 10,000 squared, 10,000 minus 5, 10,000 plus 4, that's going to give me a positive times a positive times a positive, positive region. What about from 0 to 5? 3. 3 squared is positive, so I'll have a positive times a negative times a positive. So that's going to be a negative region in there. So those of you are like, all right, let's just go every other. Watch this. So -2. -2 squared is positive. -2 minus 5 is negative. And -2 plus 4 is positive. So actually, this is a negative region. So back-to-back negative regions. So it's not always oscillating between those regions. And then -10 million squared is going to give me a positive. -10 million minus 5 is negative. -10 million plus 4 is still negative. So that will be a positive region there. All right, well, they're asking us for, right here, regions less than 0. So that's going to be between here and here. So what you got to think about now is you got to think, okay, is it from here all the way through? Well, we got to think about this. What's going on at 0? If you actually use the value of 0 and plug it in, that would give you a 0 on the left side. And that would say 0 is less than 0, which is not a true statement. So we have to kind of go to there, and then we got to go again to here. So the actual interval notation would be -4 to 0, and then union 0 to 5 for this one. Again, if we pull up this graph of this one, which I have right here, you can see how this is graphed. Like this graph is coming up, and it's just touching at that 0, and it's coming down, and then it crosses again. So you can see the actual values up here, that have a greater than 0. So less than 0 would be from right here to right here, and then union here to here, not including the 0 because it's actually equal to 0. And once again, you would be able to graph that and notice that as well. All right, I am going to stop this video because when they get too long, they get really hard to upload, so I'll come back with the next two examples.